In this lecture, we'll talk about oscillatory motion and simple harmonic motion. So what is an oscillation? So oscillation is any motion that proceeds back and forth over the same path. Okay, for example, let's say you started from some point and you walked from point A to point B, and then you came back again at the same point, and then you moved to point B again, and then back again to A, move to point B and back again to A. So this kind of back and forth motion is called oscillatory motion. And not all the oscillatory motions are periodic. Okay, periodic means, let's say it takes time t to go from A to B and then back to A. Okay, so in the first instance you may take, let's say, 2 minutes to go from A to B and back to A. And then in the next instance you may take a different time, so you may take 1 minute in the next instance to go from A to B and then back to A, and in the next instance you may take 4 minutes to go from A to B and then back to A. So this is non-periodic motion. But there are some motions in which the oscillation is periodic. Okay, so you take exactly same time to go from A to B and then back to A. Okay, if that's the case, then this kind of periodic motion in which the time period is always same is called simple harmonic motion. Okay, so let's see an example of this kind of oscillatory motion. You have a ball that is disturbed from its equilibrium position. Okay, so this ball has this equilibrium position. As long as there is no disturbance, the ball will remain in this position, which is the stable equilibrium position. But if you slightly disturb this ball, because of this net force, the ball will move back to its original state or equilibrium position. The marble that is free to roll inside this spherical ball has this equilibrium position, which is the bottom of the ball, where it will rest with no net force on it. But if the marble is pushed away from equilibrium, the marble's weight leads to a net force. A part of this, a component of this weight, will provide the net force, which is directed towards the equilibrium. So this acts as this net force. Again, this net force comes from the weight, acts as a restoring force that restores it back to the equilibrium position. Okay, so when it's moving towards the equilibrium position, it will overshoot and it will go to the right side, and then again there would be this net force pointing to the left that will bring it back again to the equilibrium position, and then it moves to the left, and then the net force brings it back to the equilibrium, moves to the right. So it does this back and forth over and over. This kind of oscillation happens in equal time interval, so it's a simple harmonic motion. This kind of simple harmonic motion is described by a sine wave, or any kind of simple harmonic motion can be described by a sine wave. So simple harmonic motion is described by this sinusoidal function or sinusoidal equation, which is a sine omega t plus phi. So here this y is the displacement of the object from its equilibrium. So this y gives us the displacement at some time t. Okay, let's say you want to find where this object is in 2-second time, whether it's here or here or here. So that's given by this equation. Okay, and this equation, this a is the maximum displacement. Okay, the farthest it can go. So this is, if this is the farthest it can go, then this is the amplitude. Like in case of spring, let's say the spring can go up to this point, okay, from its equilibrium, then this would be the amplitude. So that's amplitude, and omega is the angular frequency. It's also called angular velocity. Let me rewrite the equation. Y is a sine omega t plus phi. So here omega is angular frequency and Angular frequency is related to the linear frequency. Linear frequency is how many times does it do this up and back and forth. Okay, so it starts from here, moves up, then back again to the same equilibrium, and then to the left, and then back again. So that's one oscillation. So again, one oscillation is moving from here to here, and then back again to that point, and then to B, and then back again to the same point. So that's one oscillation. So frequency is how many such oscillations are completed in 1 second. So number of oscillations per second. And the angular frequency is how much angle it makes in 1 second time. And we also know the time it takes to make one complete oscillation is time period. So T is time for one oscillation. So the relationship between time period and frequency is 1 over T. So this equation is basically a sine equation. So that's displacement from the equilibrium, and this is time. So this distance is amplitude, and the time to make one complete oscillation, this from starting from here to here, is one complete oscillation. That is the time period. And frequency is basically how many such complete cycles are made in 1 second. Okay, a number of oscillations per second. So for a spring mass system, when it's oscillating under gravity, when it's moving up and down, so its time period is given by this formula. It's 2 pi square root of m over k. So here m is the mass of that object, hanging mass, or sometimes it could also be on the horizontal plane. In that case it's not hanging. Okay, it's just the mass attached to the spring. And k in this case is the spring constant. Okay, spring constant, we already talked about this in the previous chapter. What spring constant is, it basically tells us how stiff the spring is. This formula gives us the time period of this spring mass system, and if I want to find frequency from that, I can just use 1 over capital T, which would be reciprocal of that. So 1 over 2 pi k over m. And if I want to find omega from that angular frequency, then it's 2 pi f. So which would be 2 pi f is 1 over 2 pi k over m. So omega, or angular frequency, is, so cancel 2 pi and 2 pi, you get k over m.